So let's begin our look at operations research with matrices and vectors. So this is more like the point of the first few sections of operations research sometimes can be about like just looking at like several ideas from linear algebra and a brief overview. So it's not about the proofs more or less, it's more about just some of the basic math from it. Anyway, you have an m times n matrix, m rows, n columns, which is given in general as A11, A12, etc. The A1n, which is your n is your number of columns. And it can go vertically from 1, 1, 2, 1, all the way to m1, because you have m rows. It's labeled like that. It's always rows and column with your organization. And at the very bottom right corner will be m row n column. The nth column, the mth entry in the nth column would be the bottom right. This generalization is very helpful sometimes as a way of just a basic picture, even though they never get extremely huge in general with like this type of stuff in undergraduate works. But it's m by n. M rows, n columns. And aij, lowercase a that is an entry on row I, column j. So in this one, that just is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 3 by 3 matrix, so A12 would be 2 because that's the first row and second column. A32 would be third row, second column, so that's 8. And a column vector is just matrix as one column, row vector same thing but one row. And the vectors, whenever it's a matrix is one column, one row, it also can be classified as a vector. And the dot product of two vectors is discussed in linear algebra as well, but here we have it displayed as you have 1 by n and n by 1 matrix, n by 1, 1 by n, and the dot product of VU would be simple, just be a V1 U1 plus V2 U2 plus dot 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 plus UN VN. And if the dot product's zeros, then they are orthogonal. But it can be undefined as well if they're different, So this is 1, 1, and this is 2, 3, 5. So the undefined, the dot product. Obviously, this one's very obvious. But regardless, it's because of different dimensions as well. 2 components, 3 components, it does not work. They need to have the same amount of components above all else. But that's one way of looking at it, but the dot product is very simple. It just gives you a numerical value. Operations with matrices, you have multiplication of matrices by constants. So when you multiply by a constant, a matrix by a constant, you just have matrix A, the general one, which is up to AMN like usual. C equals constant, so C times A, you just plug in C times A11, C times A12, eventually C times A1n, and so on. Addition and subtraction is very simple as well. You have m by n and m by n, same dimensions, basically. They have the same exact configuration, basically, in general, the same layout. Just different values in them, usually, when you do this. So a plus or minus b would be a11 plus b11, or minus, depending on which one it is, plus or minus. Same with a1n and b1n, and so on. And if you have a 2 by 2 and 3 by 3, it's undefined as sum of them, the addition. Because they have different dimensions. So I think this is pretty self-explanatory so far. Transpose is a little bit simple as well when you think about it. So you have A m times n. The transpose of A is an n by m matrix. So the best way to think of it is that you're just swapping rows and columns. You make the rows columns and the columns rows. So here's a row, A11, A12, A1n. now it's a column, A11, A12, A1n. Then A11, A21, AM1 becomes a row. A11, A21, eventually AM1. That's how it works, as you can tell. But yeah, the columns become rows and the rows becomes columns is one way to just remember it in general for a transpose. We have matrix multiplication as one other operation. And the last one, I believe, significant one we'll talk about. So if you have AM times N and B, K times L, so matrix A, matrix B at these dimensions, C equals A dot B, or A times B, I guess it's multiplication. But it's very similar to the dot product in how it works. It's more like a bunch of little dot products, if you will. A times B is defined only if N and K are the same, N equals K. So that means, row times column, so column N. So basically columns of A, it has the same number of columns in A as B has rows. Yeah, because it's row by column, row column, row column. So M rows, N columns, K rows of B, L, cursive L here, I put a cursive L. L columns of B. And C will be M rows, L columns, if that's the case, if N equals K. So, and you also have Cij, which is equal to row I of A dot product column J of B. So this is like should be a lowercase c sort of. But regardless, it gets to the point. Basically, you have the entire row of one row times the dot product of another column. That's why the row and column vectors kind of matter, since you're kind of doing this miniature. You're basically doing tiny, you're doing dot products repeatedly for every entry. It's a dot product. So Cij, as shown here, can be sort of like that, and it is here. Or each entry is the summation, The summation symbol is a fancy way in math of doing it. If you actually were a pure mathematician, it would matter a lot more, like to be able to write it in a summation form. But yeah, generally speaking, you multiply row by column. And it's seen better in an example. So, and in general as well, A times B does not equal B times A. These matrices, it's not commutative. So A equals, so if you have 2 by 2 matrix here and a 3 by 3, it's undefined. It's one case of it. 2 by 2, 3 by 3. So 2 does not equal 3, so you can't do it. And it's a very important concept, that general rule. No, sometimes A times B and B times A can be the same, but it's not a common thing. You don't usually see that. The rule, it's a lot more common that they're different. So now a few examples of all these operations. That's all we talked about. So we have these matrices, these two, and we're going to do stuff like do 6 or so, 7 operations, so if it's possible. So negative A is just basically -1 times this purple matrix A. That's all you do. You basically distribute -1 times each of them, so it's just -1, -2, -3, etc. 3 times A, you just do 3 times it, so 3, 6, 9, 12, 15, 18, 21, 24, 27. Looks like a 3 times table. A plus 2 times B, so I even showed 2 times, you just multiply it in, but it still does not change the fact that it's undefined. 3 by 3 and 3 by 2. They need to be the same exact dimensions, 3 rows by 3 columns, both of them. They'd have to be the exact same. But we don't have that, so undefined. The transpose of A raised to T. So you flip the rows. Oh, that should be a T there, but it's not, or whatever. It should be this matrix raised to T for E. That's also a transpose, but minor gripe, minor mistake, it ain't gonna kill anyone. You know, just for future reference, that should have been a T there, but I just realized that now, so we'll just roll with it. But yeah, transpose, these are two transposes of each matrix, so 1, 2, 3 becomes 1, 2, 3 column, 4, 5, 6, 4, 5, 6, 7, 8, 9, 7, 8, 9. Yeah, you have your transpose, it's just... And B, so this transpose 1, 0, 1, the row is 1, 0, 1. Or I should say actually do 1, 2, row 1, 2 becomes column 1, 2. 0, negative 1 becomes 0, negative 1 downward. 1, 2 becomes 1, 2 downward. That's all you do. Row becomes column. Each of them. That's one way, that's how you do it. It's the easiest way to think of the transpose. So A times B, we'll do multiplication, so it's the matrices. So as I said, mini dot product, so purple and blue here. 1 times 1 plus 2 times 0. So it's row 1, so basically the first entry. This is one entry. 1 times 1, column 1, row 1, column 1 for entry 1, 1 for row 1 column. Then row 1, column 2. Row 2 of column 1. Basically, that's how it works. So 2 times 0 plus 3 times 1. So row 1, column 1. That's all you do in dot product between these two. And that's it. It's in space, and then it's like next entry. 1 times 2. That's row 1, column 2. Plus 2 times negative 1. Row 1, column 2 again. Then one more, and continues so on. 3 times 2. So that's one more entry. So we have entry 1, 1. If you said it would be like C little c 1, 1 and C 1, 2. So you have your first row done. And that's it. And you can do this because it's a 3 by 3 and a 3 by 2. So A first. So row, 3 rows, 3 columns. So it's columns and then row. So column, row. Like in this case, you have rows, 3 rows, and 3 columns for A. 3 rows, 2 columns for B. So 3 and 3 touch. You're next in line. So it's equal to each other. A has the same amount of rows as B has columns. That's why you have to position it right. It asks for A, B, so you have to do it exactly like this. So you continue that process of dot products, and then you multiply and then you add together everything, basically, and you get your 6 entries. So A times B is 4, 6, 10, 15, 16, 24. And the final one is B times A, which is undefined. Yeah, you have a 3 by 2 and multiplied by a 3 by 3. So 2 does not equal 3, so it's undefined and we can't do anything. It does not exist, as it would be, as you could also say. But no, it's undefined, really, is the proper way for this. Undefined. And that's it for that.